information is available at our fingertips, and many facts seem to be common knowledge, it is hard to think that at one point in time, people did not understand the information we take for granted today. How did the ideas of atoms evolve over time? How were their properties discovered? Back in the Greek era around 460 BC, there was a Greek philosopher, Democritus.
As a philosopher, I was curious about the world and what it was made of. I found and believe that there are these small building blocks. I call them atomos. These indivisible atomos are small, hard particles that have shape, mass, motion. However, they do not have other qualities like flavor. Everything is made of atomos. They cannot be created nor destroyed, only changed. Nothing exists except atomos and empty space. Everything else is opinion.
Even though Democritus came up with the ideas of the atomos, or atoms as we know them today, not everyone in his time agreed with what he proposed.
Matter isn't made of atomos, it's made of different combinations of the four elements: earth, water, air, and fire. There's no proof for these atomos. Democritus was much mistaken, and people saw my side, as I was much more popular than he. Democritus' ideas will be forgotten, and my superior knowledge will be with the people.
Aristotle's ideas were seen as superior in ancient Greece for a long time. Today we know that Aristotle was incorrect about his predictions.
In 1803, I came up with the indivisible solid sphere model. In this model, I show that an atom is a solid sphere that cannot be divided up into smaller particles. Through my experiments, I have determined that all atoms of a single element are identical. Atoms of different elements can be told apart based on their atomic weights, and atoms can neither be destroyed nor created in a chemical reaction.
Dalton's discoveries supported Democritus' atomic theory while also making modern chemistry and physics possible. Some of his theories were wrong, but they set the baseline for other scientists to come.
In 1886, I sent an electrical current through a gas discharge tube that had a perforated cathode. This produced luminous rays, which in turn led to the discovery of anode rays.
The discovery of anode rays led to the eventual discovery of the electron. Along with a discovery of anode rays, Goldstein is also sometimes credited with the discovery of the proton.
In 1897, I used what Goldstein had found and started a series of 3 experiments with cathode ray tubes, which led to my discovery of the electron. And since I knew of them, in 1904 I was able to make the plum pudding model, which shows that atoms have a similar structure to plum pudding, with tiny negative charged electrons embedded in the positively charged substrate.
In 1909, an American physicist named Millikan wanted to further the knowledge of the electron.
I wanted to measure the charge of an electron. I made a device that had 2 electrically charged plates at the top and the bottom. I then dropped a small amount of oil into the top and adjusted the voltage to see how much charge the electrons had. The positive electrons fell at a constant rate, while the negative ones slowed down, stopped, or floated upwards. That is how I discovered the charge of electrons.
A couple of years later, Rutherford started his long journey in physics.
In my lifetime, I made many contributions to science. My first one was in 1911, when I came up with the nuclear model that showed that the atom was mostly empty space with a tiny, dense, positively charged core called the nucleus, with electrons orbiting it. To prove my theory about the nucleus, I conducted a series of tests called the gold foil experiment from 1908 to 1913. I bombarded gold atoms with alpha rays. If an atom was mostly solid, then most of the rays would have bounced off. Instead, a majority of the rays passed through the atom, with only a few bouncing off the nucleus. This proved that the atoms are mostly empty space. In 1913, I added the protons to my model and renamed it the planetary model.
In 1913, I expanded upon the planetary model of atoms. Basically, if you see here, electrons do not move about randomly. They have definite orbits at some different energy levels. So the electrons in this orbit will have a different energy level at those in this orbit, and so on and so forth. When jumping from one orbit to another with lower energy, a light quantum is emitted. This means that when energy is released, light appears.
Rutherford proposed an atom with a small, dense, positively charged nucleus around which a negatively charged cloud of electrons orbited like planets around the sun. Bohr met Rutherford the following year and ended up spending 4 years in Rutherford's laboratory at Manchester University working on a new model for atomic structure. On March 6, 1913, Bohr sent a paper to his mentor Rutherford describing how his new model for atomic structure explained the hydrogen spectrum. Most of the scientists predicted that electrons moved in an organized fashion. Later, some scientists switched their focus from the electrons to other components of the atoms, one of these scientists being Chadwick.
I was a prisoner of war during World War I. They attacked some guards and let me use some things to conduct experiments. When the war was over, I continued my experiments with better technology. I was working with particles and observing the radiation. There are some particles with higher radiation. Some scientists believe this to be because of the high-energy protons. However, I was not completely convinced. I believe there must be some neutrally charged particles as well. I continued experimenting and found my theory to be supported. May of 1932, I announced my discovery of the neutron.
Two years later, Chadwick even won a Nobel Prize for the discovery of the electron.
I realized that electron orbits behave a bit like waves. If waves can behave like particles, can't particles behave like waves? Now, when a string of an instrument is plucked, only half waves are possible because of the two fixed endpoints. If a circular orbit has a fixed radius, then there can only be odd numbers of wavelengths. The relationship is shown in this equation, where the wavelength equals Planck's constant over mass times velocity.
Today, De Broglie is best known for his research on quantum theory. He is also known for predicting that electrons in an atom move in a wave-like motion in their orbits. He was later given the Nobel Prize for Physics in 1929 for his advancement in physics.
I took the planetary model by Bohr one step further. I was able to apply my findings to atoms of other elements. Bohr's model could not do this. It's called the quantum mechanical model of the atom. It's like Bohr's model in the fact that it does not define the exact path of an electron, but in fact can predict the odds of its location, or orbitals. See, this means that we can't figure out where the electrons are exactly, but we do know that they could be in a cloud of space, giving this model its name, electron cloud model. It gives a margin of error. Here starts the concept of sub-energy levels. A sub-energy level is like an amphitheater. You see, the farther away you get from the stage, or center of the atom, the more space there is for the electrons.
Humans have long been curious about the world around them and how it works. Many ideas have been proposed, tested, and proven or disproven. New scientific discoveries are being made constantly, but without these scientists, along with many others, we would not be where we are today.